Now we will be learning about aperture antenna or as antenna aperture. So as discussed in the earlier classes or as earlier session, we have the transmitting antenna and we have the receiving antenna. As we all know, the signal which is transmitted by the antenna will be maximum in relevance to the signal which is available at the receiving antenna. The main reason is whenever a signal get travel or transmitted from the transmitting antenna, it first of all radiates into free space, and the signal whichever is able to be reach the receiving antenna, only those signals will be processed. But it also depends upon the angle at which the receiver has been placed and the location where the receiver has been placed, and whether the receiver is placed at different height or whether the receiver is placed at a lower height. So whenever the reception of the signal has to take place, the receiver antenna, at one particular point of the receiving antenna, the signal received by the antenna is maximum. And that area where the signal received is maximum is called as an aperture. So it is called as effective aperture, or as it can be simply called as aperture of an antenna. So aperture can be defined as the area through which the power that is radiated is received is maximum. Like suppose I given a few of the examples were given in the earlier sessions, that the mobile which we make use also consists of an antenna. So suppose if you are staying in a residence which is located in second floor, as the obstacles in the surrounding are less, the signal strength what we have, which we get in the mobile is more, and the signal clarity is also more. But suppose if I take a situation where we would stay in a ground floor house, and during that time we can see that some of the sometimes the signal will get deteriorated. Means the 5 signal bars which will be there on the mobile phone will not be there because the tower and the distance where we are located with the antenna will be varied. Means we are away from the tower location, because as all of us know, normally the tower which is used for which is used for cellular communication, they are mounted at a higher altitude. It is not at the ground level, it is at the higher altitude. Normally they select the buildings whichever has the greater height, because whenever the antennas are mounted upon the tall topmost buildings, then the obstacle or is the attenuation of the signals will be less. So that's the purpose why the network service providers, they choose the location where the height of the building is more to install the tower, so that to reduce the percentage of loss by the transmitter end. Okay, so here also it means the same, where we can relatively compare the effective aperture of an antenna, like how we compared the signal available at the house or else when we are in second floor, and relevant to the signal which is obtained when we are in the ground floor. Normally it happens in a densely populated city, not everywhere, only in densely populated city and where the tower is not near, we come across these problems. So in the same way, whenever there's a signal that is transmitted, that is radiated from the transmitting antenna, the entire signal cannot be received by the receiver antenna. But there is one particular area, some particular area on the receiving antenna where the signal received by the receiver will be maximum. And that location is what we call it as effective aperture of an antenna. And here To have maximum effective aperture for an antenna, what we normally do is we take care such that the input power given for the transmitter is very high so that it can travel for longer distance. So this is the antenna. This is the on type of antenna which is placed in H plane, and if I have the antenna which is on the receiver end, then at this particular location wherever the antenna signals received by the antennas are more, then that location or that place is called as aperture the antenna. So the concept of aperture can be well defined in terms of area. So aperture of an antenna is the area through which the power is the power is radiated or is which is received. So the concept of apertures is simply considered at the receiving antenna. So this is the example of an horn antenna where this is on the transmitter end, and here we can see that this is power absorbed and this power where the maximum effective aperture is available. This is what we call it as effective aperture. The dimension where the signal at its maximum is called as effective aperture. Suppose if I take an example of a short dipole antenna, then the effective aperture will be only this much, because in a dipole antenna, this is pole 1 and this pole 2. Normally the pole 2 will be grounded. So whenever the pole number 2 is grounded, normally the radiation of the signal takes place only in pole 1. So that's why the maximum radiation is, the aperture value is less for a short dipole antenna. That's the reason why we normally choose the horn antenna or parabolic dish antenna to get maximum gain and to have maximum effective aperture. And one more thing is, to have the effective aperture to be maximum, normally we choose that such that the transmitting antenna and the receiving antenna are of same type. If they are different, the apertures will change. So for that reason, what we do is normally we choose the antenna where the transmitting antenna and the receiving antenna are of same type. That is, at the transmitter, if we are using a horn antenna, at the receiver also we make use of a horn antenna itself. So this is about the effective aperture of an antenna or as maximum effective aperture. And there are few more apertures which is called as the effective aperture, the scattering aperture, loss aperture and collective aperture. There are four different types of apertures in relevance to antenna. So the first one is effective aperture, which you learned now. It is the ratio of effective power to the power density. Effective aperture, we have four types of apertures which we can study. One is the effective aperture. The next one is the scattering aperture. Scattering aperture. The third one is loss aperture. And the fourth one is collective aperture. So we have come to know what is aperture, and the effective aperture, it is the ratio of effective power to the power density. It can be expressed in terms of expression, that is effective aperture AE is equal to effective power, that is WR divided by P, which is I square into RT divided by P. So maximum effective aperture for the antenna can be defined as AEM is equal to V square by 4 P into RT, where V square is the total electric field, P is the total power received, and R radiation resistance of the transmitter end. So this is one way how we can define the effective aperture of an antenna. That is AEM. This is called as maximum effective aperture. That is AEM is equal to V square divided by 4 into P into RT. The next one is scattering aperture. The scattering aperture is the ratio of power radiated or as the scattered power to the power density. So the scattering aperture can be expressed as AS, where I square into RR divided by P. That is, I is the current through the antenna, RR is radiation resistance of the antenna, P is the power transmitted from the transmitter. So in the same way, we can also define the loss aperture and we can also define the collective aperture of the antenna. So these are the 4 types of apertures which is present in the, and the last one is physical aperture. The physical aperture always depends upon the physical connectivity of the antenna. That is, it basically depends upon which is the type of antenna. Whether it is an on type of antenna, which is used as the transmit and the receiver, or as whether it is a parabolic type of antenna, or as whether it is a dish type of antenna. So, like this, the physical aperture is the concept which is studied when depending upon the physical structure of the antenna, or as depending upon the shape of the antenna. So this is about the effective aperture of an antenna and the different parameters of effective aperture. So after effective aperture, the one more important key point about the basic parameter of an antenna is effective height. Like how we have the effective aperture, the effective height of the antenna is also very much important. So what is effective height? We cannot implement the antenna in accordance to our wish, but always the height of the antenna is also one of the parameter which depends upon the frequency of the antenna. And as we know, the frequency is equal to C by lambda. The frequency is always inversely proportional to the value lambda because they are interdependent. If the frequency increases, then the lambda has to decrease. If the lambda increases, the frequency has to decrease. They are relatively dependent. So, whenever we are installing an antenna, the height of the antenna is also very much important. But we don't call it as simply height, but we call it as effective height. Because the effective height is an important parameter because if I implement an antenna which is about 10 meters long, or else if I implement an antenna which is about 5 meter long, basically it should help me that what is the propagation that the antenna can provide. So that is the important parameter why we call it as effective height. The height of the antenna may be 5 meter or the height of maybe 10 meter. Whether this can propagate the signal effectively. That's the reason why we talk about effective height of an antenna. And this effective height of an antenna is an important parameter which is related to the apertures once again. And effective height can be derived by the equation HE is equal to V by E, where V is the induced voltage and E is the electric field. And always the effective height of an antenna provides an indication of how much is involved in transmission or reception. So to understand the effective height of an antenna concept in a better way, let us just take an example of two different antennas of two different lengths. So here we have considered a short dipole antenna. This is a short dipole antenna which we have, and the length of the antenna is taken into consideration, where the length of the antenna in the diagram 1, in the figure A, it is length of the antenna is lambda by 2, whereas in figure B, the length of the antenna is lambda by 10. So lambda here stands for wavelength of the antenna. The total wavelength divided by 2 is the length of the antenna here, and here the total wavelength divided by is the wavelength of the antenna. So when we have a antenna which is of the length L is equal to lambda by 2, the effective height of the antenna is 0.641, 0.64 times the length of the antenna. Same way, whenever the antenna length is lambda by 10, then the effective height which is calculated by the formulas will be 0.5 times of the L. What is the conclusion that we obtain here is, as the length increases, the effective, as the length decreases, the effective height also increases. But whenever the length of the antenna increases, the effective height decreases. So here you can see in this demonstration, here we have taken the short dipole antenna which is of length lambda by 2. So for a short dipole antenna of length lambda by 2, the current which is obtained is 0.64 times, that is of L. This is 0.64 L. This is what we call as effective height of an antenna. Means the effect of radiation is maximum for the entire length of the antenna, where the average current is, average power is 0.69 times of the length. But whereas when I consider the where the length of the antenna is lambda by 10, this is then the effective height is 0.5 times of the L. So here we can see that the radiation pattern which has been obtained, or is the current field or the electric field which is obtained, is a tapered type. The percentage of slope of the signal is more. It cannot radiate maximum, but here the radiation is maximum. That's why we call the maximum effective height of the antenna is always dependent upon the value of length. As the length increases, the effective height decreases, but as the length decreases, the effective height increases. So this is the conclusion of the effective height of an antenna. So the effective height of an antenna is one of the important parameter which provides the information about what should be the height of the antenna for that specific application. If the antenna is high, the frequency transmitted is less, but if the antenna height is low, the frequency transmitted is high. That is what we need to keep in mind. So that's why nowadays, whatever the towers we see, which are the types of towers that we see, we normally don't see the pole type of antennas, but we see the circular types of antennas. Because the circular types of antennas have lesser length, so that it can radiate maximum. Or else the effect of radiation is maximum, or else the effective height is maximum. So when we are installing an antenna, we should keep in mind that the effective height of the antenna should be greater compared to the length of the antenna, because the entire antenna whichever is installed on the tower should work for the complete height that has been installed. So this is about effective height of an antenna. And relevant to the examination point of view, this would be asked as a short answer question. Explain the concept of effective height with an example. So the expect first of all, the basic information about effective height has to be given. Then write the structures of figure A and B. That is, consider the antenna of length L by lambda 2 and the antenna of length lambda by 10. Write the equation for effective height and finally write this diagram. This fetches 6 marks. There is no particular definition which we can give for effective height, but only thing is we need to write the equations and express it. So it is a sort of a simple justification type of answer which is expected by you in exam.